On May 18, 1980, a natural disaster shocked the country. It released more energy than Hurricane Katrina, demolished over 200 square miles of forest, and took 57 lives. Now, almost 40 years later, the long-term impact of this event can be analyzed. This is the eruption of Mount St. Helens.
Mount St. Helens is located in southern Washington near the Juan de Fuca and North American Plate boundary. As the tectonic plates push together, the Juan de Fuca plate is subducted by the North American Plate. It melts as it is pushed towards the Earth's mantle, and as the magma rises, pressure builds, creating a volcano.
Scientists knew that Mount St. Helens was a volcano, but it had been dormant for over 120 years. Minor earthquakes began about 2 months prior to the 1980 eruption, which were detected using a seismograph. A seismograph records the amplitude and frequency of waves from an earthquake. From these earthquakes, scientists predicted the eruption, but lack of data on events like this meant they had no ability to predict the severity or exact date of the blast.
The eruption was finally triggered by a larger 5.1 scale earthquake on May 18, 1980. The preceding event happened in 4 main stages. First, the earthquake caused a massive landslide in the north side of the mountain, the largest in recorded history. That allowed pressure to be released in a lateral blast of rock, ash, and hot gas. The lateral blast was powerful enough to displace nearby Spirit Lake, forcing lake water as much as 850 feet up the nearby slopes.
Then, the Plinian eruption stage began, releasing a huge plume of rock and ash from the top of the mountain. This was accompanied by pyroclastic flows as a superheated mixture poured from the crater. Snow and ice was quickly melted, creating devastating lahars or mudslides that caused more damage to the surrounding area.
A quiet zone extended for several tens of miles around the volcano where the blast could not be heard. The quiet zone phenomenon occurs because sound waves travel faster in warmer air and tend to be refracted towards cooler temperatures. The sound waves that radiated out of the volcano were bent upwards toward cooler air at higher altitudes, then refracted down due to the sun-heated air in the middle levels of the stratosphere. The sound bounced between the surface and the upper atmosphere multiple times, creating several zones of loud and quiet at increasing distances from the volcano.
Ash continued to billow out of Mount St. Helens, causing complete darkness in areas surrounding the volcano. Afterward, the direction and scope of the lateral blast could be identified by the direction of thousands of felled trees.
Conservation involved the clearing of these dead trees, especially those impacting the tidal river. Reforestation involved individually planting new trees deep in the soil so the roots could absorb nutrients beneath the ash layer. Ash also had to be cleared from the surrounding towns, and compensation was given to farmers who lost usable land.
As time progresses, life surrounding the volcano is starting to get back to normal. Forests are thriving, and shifted populations are becoming more naturally regulated as predator species return. Many local streams are back to pre-eruption conditions. The speed of recovery has surprised even those in charge of conservation efforts.
Now, Mount St. Helens has the best seismic monitoring network of any volcano in the Cascade Range. It continues to be active, with the most recent eruptions being in 2006 and 2008, though they pale in comparison to the 1980 event. Close monitoring of the lava dome reveals that it fluctuates in size depending on the seismic activity. This is an incredibly useful surface-level predictor.
Though the 1980 eruption of Mount St. Helens was a tragedy, it offered scientists an unprecedented example of how wildlife can recover in a completely devastated area, and new seismic monitoring methods developed as a result of the blast. This means that future events can be predicted with much more accuracy.